Okay, good morning everyone. So I'm continuing. So I'm still using the lecture notes. And today I want to do a few things. So very briefly first, it's about chemical potential on the lattice. One reason to discuss it is because there's an interesting observation that follows from that, which I'll need later on. And then we'll look at the phase diagram at small mu. And then the third part, which will take the longest and will carry over till tomorrow, is the basically an extended discussion of the quark mass dependence. Center symmetry. And imaginary mu. So these three things are all related, and they fill up the phase diagram in quite a nice way. Where is it? So first, are there any questions about yesterday that you want to ask now before the... Not, you can ask in the lunch, of course, as well. But. Okay, so the first bit, chemical potential on the lattice. So what have we seen yesterday? We saw that first, mu couples to the conserved charge, of course. That's essentially by definition of what mu is. And the second observation is that mu appears as the imaginary component of the fourth component, temporal component of a gauge potential. So if I'm in Euclidean space, it appears as imaginary component of A4, say the vector potential A4. And these two things are the guidance on how to introduce mu in a lattice theory. So I don't expect you to know really anything about lattice QCD or lattice fermions, except just to say that the fermions live on sides. So I have two sides here, x and x plus nu. Then the fermion fields live on these sides, so I'm calling them psi x and psi bar x. And the gauge links live between these sides. So here's a u, which I'll denote with an x and a nu. So it goes from point x to point x plus nu. And the way these fields transform on the gauge transformation is as follows. Psi of x goes as, this is a gauge transformation, psi x. Psi bar of x goes as psi bar omega dagger. And the gauge link transforms as omega x u x nu omega x plus nu dagger. So u here, omega here is an element of SU3, and so omega dagger omega is one as a unitary matrix, and this is how the fields transform in on the gauge symmetries. This is what you expect. Say in abelian theory, this would just be the phase factor e to the I alpha. Is a local transformation, and e to the I minus alpha, and these links transform in this way. Now, if we combine these things, and we know that the fields live on these sides, it's easy to come up with gauge invariant terms. So we could have, say, a field at side x, then a gauge potential going from x to x plus nu, and then a field at psi x plus nu. Exactly as I've drawn here. And this combination is gauge invariant because this transforms with omega dagger, this transforms with omega on the left, omega dagger on the right, and this again with omega at the next point. So this thing is gauge invariant. And now if I take the limit, and so other gauge invariant terms are of course terms that live on the same side, psi x bar psi x, because this is also the omega and the omega dagger just cancel on the same side here. So these are gauge invariant terms. Now, if I want to implement a derivative, so something like d nu of psi, then in a discrete system, this means I have to do I write it as the difference between two nearest neighbors, say in this way, where A is the lattice spacing, and so this is simply a nearest neighbors difference, so a discretized derivative. And typically I will actually use the notation where the lattice spacing is put to 1, so I would just write it as a finite difference. So the kinetic theory will consist of these differences, and therefore of these kind of neighboring points here, fields at neighboring points with a gauge a term in between, gauge link in between to make it gauge invariant. Now, how did we introduce chemical potential? It was something of the form psi bar, gamma nu, d nu, minus or plus I a nu if it's an abelian field, plus mu gamma 4 plus m times psi. So it is this, so as I said there, it couples to the charge in the continuum psi bar gamma 4 psi, and it appears just like, it appears with a gamma 4 matrix, so just like the fourth component of a vector field. Now, if you do this naively, if you now take this kind of action and you introduce chemical potential simply coupled to something like, say, mu psi bar gamma 4 psi, then that turns out not to work. So that you can try this, but it doesn't work. And how can you see it doesn't work? You get new divergences, new ultraviolet divergences, when you just look at perturbation theory. And you don't expect that. You don't expect ultraviolet divergences once you introduce a chemical potential. Because the ultraviolet divergences are determined by the physics at short distances, and that should be the same whether you're at zero temperature or at finite temperature, or at zero chemical potential or finite chemical potential. Temperature is kind of obvious because temperature corresponds to the compact fourth dimension, so that's an infrared property. It's nothing to do with ultraviolet length scales. And for chemical potential, we'll show in a minute that actually it's also an infrared property related to the compact fourth direction. So this doesn't work. And so we have to take the inspiration actually from the second point there, namely that mu should be the fourth component of a vector potential. And I've just argued here that how do vector potentials appear in the action? Well, I haven't said it explicitly, but these links U here are essentially e to the I a x nu. So they are the Wilson, like Wilson lines between two neighboring points. And so the vector potential doesn't appear in a linear way, like in the continuum, but actually appears in the exponent. And so if I want to treat the chemical potential as the fourth component of a gauge field, it's very well argued that I should introduce it in the exponential, like this, and not in a linear way, like here. So the suggestion is to use it as an exponential, introduce it as an exponential. So we want to introduce this as e to the mu or e to the minus mu. And I'm using lattice units throughout. So mu is actually shorthand for A times mu. Mu is a chemical potential, it's an energy, so it has dimension of energy. So if I multiply it with a lattice spacing, it's dimensionless. So this would be a dimensionless combination, but I won't write the hat on there and just write it as mu. So this should always be understood as e to the a mu, or e to the minus a mu. So I want to introduce it as a vector potential, which appears in the exponent and appears between two nearest neighbors. And so if I do that, I end up with the term as follows. So in the action, I have terms of the form psi bar x. So let's write just down the fourth component, x for, and now I write here an e to the mu, gamma 4 psi x plus 4, and I have a backward hop c bar x plus 4 u dagger x 4 e to the minus mu gamma 4 psi x. So these are two of these links in the time direction. So let me point it upward to present this time. So this is x. This is x shifted by one lattice spacing in the time direction. There's a link in between to make a gauge invariant. And then the chemical potential is multiplied in as well. So there's an e to the mu here. And for the backward link, so this is to make the action Hermitian, well, when there is no chemical potential, I start at the point x plus 4. I go back, which means I have a u dagger going in the opposite direction, and there's an e to the minus mu going down here. Of course, we only introduce it in the temporal direction because it's the imaginary component of a gauge potential in the fourth direction, so space terms are not affected, and in the same way the mass term is not affected. So now you can check a few things. First, the conserved charge. Indeed, if I differentiate with respect to mu, I get the conserved charge, which is of the form psi x u x4 e to the mu, well, the same expression basically, but with a plus sign in between. So same expression, and then, well, let me do it the other way around. Let me first take the naive continuum limit. So if I take the continuum limit, so in a naive, what do? I take e to the mu, e to the plus or minus mu. Remember, this was in lattice units, so this was actually e to the plus or minus a mu. So if I expand this out, then this will be 1 plus or minus a times mu plus higher order terms. So I get a term linear in mu, which is what I expect from the continuum theory. And if I take this expansion, I can actually also expand these differences here between x and x plus nu and expand them out. And so I'll end up exactly with psi bar x gamma 4 psi x times mu. So in the naive continuum limit, I exactly get the chemical potential coupled to the continuum charge density by taking the lattice spacing to 0, so shrinking this length here to 0 and expanding this exponential. And the second thing is that this mu couples to the conserved charge. And this is true even at finite A, so on the lattice. So we don't, chemical potential does not emerge in the continuum limit. Yeah.
Excuse me, I'm a bit confused by this indices. So where does X go?
Okay, so X labels the sides on a lattice. So if I have, so say this one side is X, then this side here is X plus one step in the temporal direction. So I would call this X plus 4. This is then in this direction, this side would be X plus 1. Suppose I'm in the X1 direction. And this side would be X plus 1 to the right and 1 in the up direction, X plus 4. The links then go between the sides, so they have two indices which indicate the starting point and the direction. So the link that goes in this direction would be X1. And then the link that would be in here, say going up, would be U X plus 1, which is the starting point, and it goes in the fourth direction. Yeah, does it help?
And if mu equals to 0, then this term is just simply the kinetic?
Yeah, so that's another good question. If I take mu to 0, and then I take the naive continuum limit, how do I do that? Well, I can write this one here, psi x plus 4. I can write it as psi x plus a times d4 of psi at x, plus higher terms. So I do a Taylor series around the point x, basically. And if I do that with these, for these terms, then you will see you get, what you get here will be psi x. This will go to, well, this will go to the, this will become the covariant derivative. So let's put the link to 1 for the moment. And then I get gamma 4 d4x, psi x minus, and then it's the same, psi, well, okay, there is a leading term here. So there is a term psi x plus d4 psi x plus psi x bar minus psi x bar 1. I have to think with the signs plus is probably, so we have to do this expansion here. So psi bar plus d4 psi bar x. And this still remains gamma 4 psi x. So this, if I expand these fields here around x, so then the leading term drops out, psi bar gamma 4 psi, which cancels again this one. But the second term will give the symmetrized derivative. We'll give psi bar d4 psi minus d4 psi bar psi, which is it's exactly the derivative term. Yeah. So it's basically taking finite differences and expanding them out around the point. You will do a little bit, I mean, the first question which you're going to do will be about the Bose gas, which is, easy, in a way easier than the fermions. But there you have to do exactly this. You have to take finite differences to expand it out and see that you get a continuum theory. So you'll do this as an exercise, actually, to see how this works. Yeah.
This naive insertion of the chemical potential, does it lead to problems in the discretization, in the naive limit, or in the physical limit as well?
No, it leads to problems in the continuum limit. So when you take the continuum limit, so you start with the lattice action, and you compute Feynman diagrams with the lattice action, which you can do because it's a field theory. And then you take the continuum limit in the Feynman diagrams. Then you find new divergences, which are ultraviolet divergences, which you do not expect.
So it's a
It's a physical problem, say. Not, yeah, so. But the source is quite clear in a way, because even at finite lattice spacing, so at finite lattice spacing, there is a global charge symmetry. So there is a conserved current, and the conserved current actually has this form of psi bar x, psi x plus nu, say. And so I should couple the chemical potential to the conserved current, and this is not the conserved current on a lattice. So this is, you could call the conserved current here a point split current, because it's, it kind of connects fermion fields at two neighboring sites. Yeah. But this is, yeah, so this is interesting, but really only interesting when we actually work on lattice QCD, otherwise it goes a bit too far. So what I want to stress here for the next 3 minutes, basically, when we finish this now, is that chemical potential appears as an exponential here, and if I hop forward in time, this step is enhanced by e to the plus mu, whereas I hop backwards in time, it's suppressed by e to the minus mu. That's what the chemical potential does. And that is another way to actually see the sign problem, is that the symmetry in time reversal is broken. Because forward moving in time is favored by e to the plus mu, whereas backward movement in time is punished by e to the minus mu. So reflection in time has been given up. And that's another way to see as it's a source of the sign problem. So I want to use this to arrive at something which will be of interest for this third part of the talk, actually. So forward hopping, so a forward step in time, Euclidean time, is enhanced by e to the plus mu. Backward hopping in time is suppressed by e to the minus mu. Now this is interesting, because now I have suppose I now think of my lattice theory as a bunch of fermions that are moving around on this lattice. I can have different possibilities. So if this is now Euclidean time, which goes from 0 to 1 over t, 1 over the temperature, which is the direction, the temporal extent, I can imagine having a fermion hopping, say, in time like this, and then closing in on itself. So making a loop in the time direction around the lattice. And suppose I have anti sites in this direction. So in this case, I would have 1, 2, 3, 4, 5, unfortunately, an odd number. But so I wrap in this direction. The fermion wraps in this way around the temporal lattice direction. Now, every forward hop is enhanced by e to the mu, and let me introduce the lattice spacing again now. So every forward hop comes with e to the a mu. And how many forward hops are there? Well, exactly nt. So this configuration will get a contribution from the chemical potential, which goes as e to the a mu times n tau. Yeah, so this is the enhancement. Now, what was a times n tau in the Euclidean formulation? Remember, a times n tau is 1 over the temperature. And so this is exactly what you would get in a theory. You don't have to refer to the lattice spacing, so it's enhanced by e to the mu over t. Now, this would be a fermion hopping forward in time. I can also have a fermion moving backwards in time in this way. And this obviously is now suppressed by e to the minus a mu times n tau. So this configuration is suppressed by e to the minus mu over t. So this, as I said, this is another way to motivate the sign problem. There's an imbalance between particles moving forward in time and particles moving backward in time, or antiparticles moving forward in time. And this imbalance is one way to view the sign problem. But then I have a third possibility. I could have, say, world lines of fermions that do not wrap around the lattice, but that simply close themselves upon themselves, like this. So what would be the chemical potential dependence of such a configuration? Zero, because I have as many forward hoppings as backward hoppings. So this e to the plus mu and e to the minus mu exactly cancel. So there will be e to the mu forward minus exactly the same number e to the mu backwards. And so this is 1. So a world line that does not wrap around the fourth direction has no chemical potential dependence. So this is quite interesting because it suggests that the chemical potential dependence has something to do with wrapping around the lattice, and in other words, has something to do with a boundary condition. And that's actually the case. So we can make that very explicit by a field definition to see that the chemical potential dependence actually is a boundary condition. Of course, if it's a boundary condition, it is not ultraviolet, it's an infrared property, which then backs up this previous statement I made that there should be no new ultraviolet divergences linked to the chemical potential. So let's make this now explicit that the chemical potential is a boundary condition. So let's see. So what terms in the action did we have? I've just erased them. We have terms of, say, form m psi x psi without chemical potential. I have terms, say, x in the space direction, gamma I psi x plus I. And then I have the interesting terms in the, so this is in space. And then I have the interesting terms in the temporal direction. Let me write them again. X, x4, e to the mu, gamma 4, psi x plus 4, and the one that goes in the opposite direction. So these are the terms that I get in the action, either a mass term or a discretized derivative in space or in time. Now these appear in the path integral, so these are integration variables. So I'm free to do a field redefinition. So let's take the following redefinition. And here I have to get the signs right, so I'm calling psi of x e to the minus mu times t. So this is at some time slice t, psi prime of x, and psi bar is psi bar prime e to the mu times t. So I do this field redefinition. Now I'm going to express everything in terms of the prime fields, the new fields. So first, what happens with the mass term if I do this field redefinition? Nothing, because this goes with e to the plus mu t, this goes with e to the minus mu t, so nothing happens. What about these terms here, where I have a finite difference between point x and another point in the space direction? Again, nothing, because they have the same, they live on the same time slice. They only differ in the space direction. but they're on the same time slice tau, so nothing happens. So the only terms that are affected are these. So let's look at the first one. So this one will go to psi prime, and then u for x, e to the mu, gamma 4. This psi bar will give me an e to the mu tau. And this one is at the next side in time. So this will give me an e to the minus mu tau plus 1, because it lives at the next time slice, psi x prime. So here I have, this is psi bar at time x, and psi at time x plus 4. So if I do this field redefinition here, I have e to the mu from the original action, e to the mu times t minus e to the minus mu tau plus 1. And so the mu factors exactly cancel. So they exactly disappear. So in terms of the prime fields, the mu dependence has completely disappeared. However, I have a boundary condition. I have to go around the temporal loop, so I cannot do this forever. And so the mu dependence pops up as the boundary condition, as I mentioned. So what was the original boundary condition? For the original field, I used periodic boundary conditions. Actually, they're fermions, so I have to use anti-periodic boundary conditions. When you derive the path integral, from first principles, you will find that there is a minus sign. So the original boundary condition, if this is point 0, and this is point n tau, so the next going around once in the time direction, there is a boundary condition like this. And if I express this now in terms of the primed fields, then I find that so psi is so psi and tau goes to e to the minus mu times n tau psi n tau prime, and that should be minus psi 0, which is just psi prime 0. And so the boundary condition I pick up is that psi prime at n tau is minus e to the mu over t psi 0, because I have exactly this factor coming up as a boundary condition. So this makes it very explicit that if I do a field redefinition, and this is the compact direction with n tau time slices, chemical potential comes out as a boundary condition. And we'll use this later on. This is why I'm telling you this. Okay, so both temperature and chemical potential can be thought of as having to do with boundary conditions in the fourth direction in the Euclidean theory. Any questions about this? Yeah, David. Why is it U for? So this should be X. So this should be X for hat. Yeah. Okay, so that's it. So it shows that its chemical potential is an infrared property, not an ultraviolet property, and it's a boundary condition essentially. Okay, so let's see. So we've seen that there is a sign problem. We cannot use standard Monte Carlo methods to solve the path integral. And so people have been spending a lot of time trying to avoid the sign problem in the kind of most minimal way. And that means restricting yourself to small chemical potential. And you can get, quite a lot of physics out of that. So let's discuss that now. So this was point 2, phase boundary at small mu. So the statement is we cannot do simulations for general mu. So we restrict ourselves to small mu. This is still pretty interesting because the phase diagram, looks roughly like this. And this axis here, this region here, is relevant for heavy ion collisions at RIC and at LHC. And so in terms of phenomenology, there's a lot of... Phenomenology is a very hard word, so I cannot talk and write it at the same time. Phenomenology. I have to say it out loud, otherwise I miss a syllable. So there's a lot of interesting phenomenology which you can extract in this region of small mu. And so this basically means small mu over t. So in this kind of wedge here, there's a lot of interesting physics to extract. Now, what can you compute here? Well, the property of the phase transition at 0 mu is by now well established, so it's a crossover. And then you can go to non-zero mu to see how this boundary here depends on mu. And so that would be, say, the critical temperature. It's a crossover, so critical temperature is not uniquely defined. But let's say you take some observable which has some near critical behavior, so let's call that the critical temperature. Then this, we can see how this critical temperature then depends on mu. And this will go with a minus sign, so it will bend downward as something like, so let me write it as 1 minus kappa times, say, mu over t squared plus higher orders. So it follows from symmetries of the path integral that it will be an even function of mu, so it will depend on mu squared. And so the thing to compute here is to compute this coefficient, say, of the mu squared term or higher order terms in this expansion. So that's something that is accessible with standard simulations, as I'll explain now. So what can we do? So I'll discuss three approaches. So the first one is to go back to reweighting. So what is we've actually already seen reweighting because it's linked to the overlap problem. So what is reweighting? We have a particle du with some weight u here. So here, this is a general weight, and what's important that it's a complex valued probability. So it's not a probability, it's a complex number, just like the fermion determinant is complex. So what could we do? We could say, so what are observables? du observables are defined in this way. So what we could try is to introduce a new weight. So let me call it R for reweight. R of W. So any weight, any other, whatever proper probability distribution, which is positive and real. So we can do simulations with this. And then it's just straightforward exercise to rewrite expectation values as follows. So say O of W can be written as with respect to this new weight. And then we have W over U divided by R over U to compensate for the introduction of this weight R times O. And we have to normalize it with the partition function. Like this. And this actually is exactly what we encountered when we looked at the overlap problem where we wrote the determinant as the modulus times the phase, because this will be an expectation value with respect to the real weight of this whole combination here, W over R times O, computed with respect to the real weight, and normalized with the expectation value of this ratio of weights W divided by R with respect to the real weight. So again, this is just mathematical rewriting, but this is exactly what we encountered with the complex phase, but this would be the expectation value of the phase factor. So if W is the Young-Mills action times the determinant, and R is the Young-Mills action times the absolute value of the determinant, then we are back in exactly the original combination, because then the expectation value of omega over R is exactly the expectation value of the phase of the determinant in the phase quench theory. So it's exactly like this. So no surprise then is that you encounter exactly the same problems as before, namely this expectation value W over R is actually the partition function with the full original weight normalized by the partition function with this real weight, which is computable. And this will also go to 0 exponentially, where the free energy, the difference of the free energy density is the free energy density of the original theory and the free energy density of the theory with the real weight. So reweighting in general, whatever measure you use to do the reweighting, will again have an exponential sign problem. Nevertheless, you can get somewhere. So this method has been used in the past. It was first used quite a long time ago, in the 1980s, and it was developed in Glasgow. So it was called Glasgow reweighting. And what was chosen here was that this reweighting factor was essentially the determinant of the fermion matrix at non-zero mu, normalized by the determinant of the fermion matrix at 0 mu. Obviously, at 0 mu, the determinant was real and positive, if you have to say enough two light flavors. So this is not quite the same as the modulus, where you have the phase factor, but very close. It's the full determinant divided by the determinant at 0 mu. Now, if you think about it in terms of the phase diagram, what are you doing here? You try to simulate at 0 mu, so you do a simulation at this point here, and you try to reweight to the physics of non-zero mu using the configurations that have been gathered here at 0 mu. So you want to reweight into the mu direction in this way. Now, what would you expect if you try this? In terms of the overlap problem we discussed yesterday. That's kind of an open-ended question. So it has a massive overlap problem, basically, because the configurations that you are sampling are relevant for the physics at 0 chemical potential, but you want to probe the physics at high chemical potential, say the physics of nuclear matter, and so the configurations that you're sampling here have essentially no relation with the configurations you're interested in. So this problem completely fails and has a massive overlap problem. So you're basically sampling the configurations you collect by sampling at 0 mu have nothing to do with the configurations you're after. So this ratio here goes to 0 very, very fast. So that doesn't work. Now, there was an improvement done, which is interesting because it tells you, shows a little bit better physical motivation. And so this is can leave this. I say overlap preserving reweighting. And this was developed around 2002 by Fodor and Katz from Budapest and Wuppertal. And here the idea in principle is quite clever. So you try to reweight not from 0 mu, but suppose you want to sample this phase transition region and you want to go to non-zero mu. What they basically suggested is that reweighting should be done in such a way that you kind of stay on this line as well as you can. Because if you stay on this line and you're in the phase transition region, your configurations will have typical configurations that are here below TC, so they will be configurations that are relevant for, say, hadronic physics at finite temperature, which will also have configurations in the quark-gluon plasma phase. So they also represent the physics of the quark-gluon plasma. So if you manage to sample configurations in this region here, you have a mixture of configurations that are relevant, irrespective of whether you go a little bit more in the quark-gluon plasma or a little more in the hadronic phase. So whereas here the configurations, in this high-dimensional probability space, the configurations are maximally separated, have no overlap. Here, maybe there is some overlap between configurations, and depending which area you go into, you go more into this direction. So there's some sense in this in which way this could work. So this is so what is the reweighting factor in this case? Well, of course, we have to make the fermion determinant real. We cannot do simulations with non-zero mu. So the reweighting, the determinant appearing in the reweighting theory will be with 0 mu, so that it's real, and we can use it for simulations. But we're also, in a way, changing the temperature here, because this line has curvature. So we also put here a change of the couplings that appear in the Young-Mills action. In a way, changing the temperature, although it's done by changing the gauge coupling, but that's not completely relevant. So by changing both, as we increase mu, we also change the gauge coupling, in other words, the temperature, can kind of try to stay on the crossover line here and preserve overlap with the true configurations there. So that was this proposal from 2002, and they actually found, in this quite a famous paper, they estimated the critical endpoint. So they did this, and they saw that, okay, there is a crossover, but then there is this critical endpoint, which they located by doing this kind of analysis. So that was, in a way, the first lattice simulation of a critical endpoint using lattice QCD, not using effective models like NGL models and so on. Unfortunately, this method is, it's quite interesting, but it was done on a very coarse lattice. And if you remember the discussion yesterday about the continuum limit, there were only 4 sites in the temperature direction, which basically tells you what the lattice spacing is, because if T, say, is about 200 MeV, then the lattice spacing is given by 1 over T times n tau. So you can compute the lattice spacing in this way, and it's quite a coarse lattice. So, and it has never been repeated either. So, there would be a real interest to go to smaller lattice spacing. So there's a lot of skepticism about this result. But nevertheless, it's an interesting idea because it tells you something about how to preserve overlap and what is possible. So this is, in a way, one of the more ambitious ways to go to non-zero mu from 0 mu. Any questions about this? Yeah.
What is never repeated?
What is?
The never repeated. Can you explain a bit again? Never repeated.
This critical endpoint? Or?
The line never repeated.
Which line? Sorry. Never repeated.
Yeah,
Okay, so it means that nobody has ever extended this calculation to larger n tau, or which means final lattice spacing. So.
It was so groundbreaking paper, and it was in 2002, where facilities were less powerful.
Yeah.
Why?
Well, let's say there's a lot of skepticism on how well this method really works. I have to switch the mic off though. So, yeah. Let's say it was an important paper to stimulate the field. But there's a lot of skepticism in general, yeah. Other questions about this? Okay, so a slightly more modest way to proceed is to, again, start with mu equals 0, and then go to the non-zero, in the non-zero mu direction by a Taylor series expansion. So this is approach number 2, which is more modest. Taylor series expansion. So let's start with the pressure, T over V times log Z. And this pressure is a function of potential. And so we can look at, say, let's call it delta P, P at non-zero mu minus P at zero mu. And this, so it's based on symmetries of the action and the partition function. It's even in mu. So this will be some kind of expansion, mu squared over 2 factorial d2p d mu squared plus, mu to the 4 over 4 factorial d4p over mu to the 4, etc. So we can simply look at the pressure as a thermodynamic variable and do a Taylor series in mu. And so I can write this, say, as delta P over T to the 4, which is a dimensionless quantity, as some series expansion. In principle, if there are no singularities, if the theory is analytical, you can just do this expansion to all orders. And then when there are singularities, that will tell you something about the radius of convergence of this expansion. Now, although this looks like quite a simple idea, you can get a lot of physics out of this. For instance, the density just follows by differentiation. The density is taking the derivative of the log of the partition function with respect to mu. So to work out all the factors, it's dp d mu gives you the particle density or quark number density, and that will just be something that is related to these coefficients again. N equals 1, 2, C 2n t, mu over t, 2n minus 1. So this will give you the density. And if you go to higher orders, you can also get, say, the susceptibility, because that was dn. The mu gives you the quark number susceptibility. So although the Taylor series looks like just something you can do, you can extract a lot of physics out of it, because there are susceptibilities, fourth order susceptibilities, which are all related to these coefficients appearing in this Taylor series. So in other words, if you can measure these coefficients or compute these coefficients, you can say something about susceptibilities, higher order susceptibilities, and so on. Now, the trick, of course, is that all these coefficients here are, of course, actually computed at 0 mu. So, because I'm doing a Taylor series expansion, and so by definition, I have to put here mu equals 0. Mu equals 0. So this is a computation that is feasible. I can compute all these coefficients at 0 mu and reconstruct thermodynamic variables which are obtained by differentiating with respect to mu to whatever order I'm able to work with. So this is a good idea in principle. However, of course, there's no free lunch, so the sign problem comes back here as well, but in a slightly different way. We've seen it before. So everything is real and positive, so the simulations are fine. But it turns out that the signal from these simulations will become extremely noisy, basically. So there's some limitation as well. So let's see how this goes. So let's look at these typical coefficients C2n. So let's write the partition function d mu e to the minus s Young-Mills that m. And I'm going to put the determinant in the exponent. So d mu e to the minus s Young-Mills e to the log that m. And of course, when I differentiate with respect to mu, which we'll do now to get the Taylor coefficients, I'm differentiating the mu dependence which appears here in the fermion matrix. So let's just work out the first few derivatives. So if I take the first derivative, if I differentiate this term, it brings down the log of the determinant, and then I have to take the derivative of the determinant and of this matrix. Yeah? So if I differentiate with respect to mu, it brings down this whole term, which then appears in the, under the integral. So I'm actually computing the expectation value of the derivative of this term. So I can write this as the derivative, the mu derivative of the log of that m, like this. So log z means there's a 1 over z to normalize the expectation value. If I differentiate z, it brings down this term. Yeah. And this, of course, continues like this. So if I take the second derivative, I get three terms, actually. So I can differentiate this term one more time. So I get dd mu squared log that m. I can differentiate another time this exponent, which appears in the expectation value here. So that gives me something like dd mu log that squared.
Isn't something missing from the first line? I mean, if you derive the logarithm and get, is this a weight with respect to the Young-Mills section or with respect to the...
Yeah, so that's why I wrote it in the exponential. So it's a weight with respect to the full weight, including the determinant. And I put it in the log so that when I take the derivative, it leaves the exponential. Yeah, so it's the full weight indeed. Yeah, good point. So now I've differentiated this term. I've differentiated this exponential again. And then, of course, I can also differentiate the numerator because this is an expectation value, so it's with a 1 over z. So if I differentiate that term, I get a square of the first derivatives, dd mu log that m squared. Okay, so the second derivative gives three terms. I'm not completely done yet because I have to compute these expectation values. So I have to compute mu derivatives of the log that so that we can work out a little bit more to see what it looks like. So log that of m is trace log of m. So if we use this, then with the first derivative dd mu log that m will give me, so the mu derivative of trace log m. And what is the mu derivative of this? That's the trace of m inverse, and then the mu derivative of m. These just, definitions of derivatives of matrices. And the second derivative is something very similar. It's the trace. So there are a few terms here. So I can, if I take the second derivative, I can differentiate this term here. So I get m minus 2 No, I'm writing it wrong. I have to do it properly. So I can differentiate this term here. So I get m minus 1 d2m d mu squared. Or I can differentiate this matrix, but I have to remember that there are matrices. So I get something that looks like m minus 1 dm d mu, m minus 1 dm d mu. So I'm using the kind of a chain rule. And remember that the m are matrices, so I have to keep the ordering intact. Now these quantities have a nice, this is what lattice people actually like to calculate. So this is something you can compute, because what is this? This is a fermion propagator. M is the Dirac matrix, so the inverse is the propagator. This is a fermion propagator times essentially a vertex. So this is something with gamma matrices, say gamma 4, something like that. And then I take the trace, which means that I'm integrating over all space-time points. So if I want to draw this as a diagram, I basically have a fermion propagator, M inverse, which starts at point x and finishes at point x. I'm integrating over all point x's. And at this dot here, there's an insertion, which is the second derivative of the fermion matrix with respect to the chemical potential. And so this is something that you can compute on the lattice quite well. This is something similar. I have here fermion propagator, some derivative insertion, another propagator, again an insertion. It's a trace, so it closes on itself. So I have two of the insertions here. So this is a m prime and m prime. And this is a fermion propagator connecting those two lines. So this is something you also encounter when you compute, say, mesons in a lattice calculation. Say this is a quark and an anti-quark closing on themselves. So these things are all fine. But the problem comes when I look at the term with a square here, up here. So this is this first derivative of log that squared, and the first derivative is this one. This again is just a closed loop like this with an m prime here in the middle. But if I square this before taking the expectation value, I find something like this. So d mu of log that m squared. If I write this in terms of these kind of diagrams, I'm actually looking at two diagrams with closed fermion loops that look like this. So this is, say, this m prime at one point. I have to average over all space-time points. Here's another m prime, and these are two fermion loops. Now this contribution in lattice jargon is called a disconnected contribution, since there are two fermion loops here which have to be estimated independently, and they only talk to each other by the exchange of gluons. So I need gluons connecting these two fermion loops. And so, for instance, in free field theory or very high temperature, this would be 0, because nothing connects these fermion lines. So this is what is called a disconnected contribution. And the upshot from this is it's extremely noisy, so it's very difficult to compute. So the first two terms are easy to compute. This is very difficult to compute. And this is in a way where the sign problem comes back in the Taylor series expansion. I've only given the result here to second order in mu. But if you go to higher order term, fourth order, sixth order, eighth order, you get more and more of these terms which contain all these disconnected contributions, which are very difficult to compute numerically. So this is kind of the sign problem coming back via a kind of way where you have to again beat the noise, but not because the weight is not real, but because the components going into the calculation are very noisy. So the state of the art here is more or less, I would say, that the order mu squared terms are fine, meaning they have been computed for physical quark masses in the continuum limit, and then the order mu to the 4 is probably almost fine, and the current status is, say, mu to the 6th, mu to the 8th, where there is still some, some work to do to get the coefficients under control. But the other mu squared term is important, so this curvature of the phase boundary here, that basically has been determined with physical quark masses and in the continuum limit, for the up to order mu squared, so that quantity is known. Okay, that's the Taylor series expansion. Any questions about this? Yeah. Yeah, so that follows from a symmetry of the action, essentially CP invariant. So at 0 mu, particles and antiparticles are the same. So, yeah.
It's the average density.
Say again?
It's the average density.
Yeah, so this is 0 at 0 mu, exactly. So this term would be odd in mu because I take one derivative with respect to mu. But at 0 mu, I'm evaluating it always at 0 mu, say. At 0 mu, the density is 0, so all the odd terms are 0. That's a good way. Yeah. Other questions? Okay, I want to say one more thing to finish this section, and then we have a very short break. It's actually linked to the Taylor series. We may not have a break, who knows? And so that is the third approach. We did reweighting, we did Taylor series. So let's briefly talk about imaginary chemical potential in this context. In a way that is kind of linked to the Taylor series. So we've seen that if I take the complex conjugate of the fermion determinant, it's not real in general, but it satisfies this symmetry. And so for real mu, the determinant is complex, but as we discussed yesterday, if mu is imaginary, so if mu is I times mu imaginary, then the matrix is real, determinant matrix is real. So the determinant of mi times mu I is real, and so you can do simulations at imaginary chemical potential. Now, why would you want to do that, you may ask? What does imaginary chemical potential mean? But what I've just erased, actually, and also related to your question, the pressure, as we said, d p mu, was an even function of mu squared. So a function of mu squared, even function of mu. So if I think of chemical potential just as an external parameter which can be changed, I can say, look at this boundary condition and say every time my fermion lines cross a boundary condition, I don't multiply it with e to the minus mu over t, but I multiply it with e to the I mu over t. That's something I can perfectly do. We can think of this expression here as a function of mu as a complex number. So I can think of this as mu with mu taking mu complex values. And then, of course, when I do this, look at, say, this expansion here as I times mu I get exactly a nice expansion again, but it will be minus mu I squared, because I take it imaginary, so I get a minus sign, plus mu I to the 4 minus some number to the 6 plus higher order. So this expansion still, is perfectly fine. I consider mu to be complex valued or imaginary. And importantly, of course, these coefficients here are exactly the same because it's the same, quantity I'm studying. I'm studying the pressure as a function of complex mu. So in other words, I also have access to these coefficients in the Taylor expansion by going to imaginary mu. But moreover, whereas in the Taylor series I can only do simulations at 0 mu, for imaginary chemical potential I can do simulations at all imaginary chemical potentials. So I have a little bit more control over the region in which I can simulate, and then the region in which I can find a relation with real chemical potential. So how can we plot this? Well, I just keep erasing the same diagram. So at real mu, we have this phase boundary. I can now decide to plot this as a function of mu squared. So that on here, on the left side, on the right side, we have real mu, but on the left side, we have imaginary chemical potential. And if we said that the phase boundary here, Tc, is a function of mu squared, then this phase boundary here will become a straight line at leading order in mu squared, like this. So we have Tc as a function of mu squared, where mu squared can be positive or negative, both are fine. And so we know that if the phase boundary curves downward here, so if Tc was something like Tc at 0 times 1 minus some number times mu over t squared, say, then we know that for imaginary mu this will change sign, so it will go upward. And so what you can do, and which has also seen a lot of success, is do simulations on this side, where the fermion determinant is real, determine physical quantities you're interested in as a function of imaginary mu, and then do an analytic continuation to real mu to see how quantities depend on real mu or mu squared on the right side of this diagram. So here the program is as follows: compute at mu squared equals less than 0. And then, so we get, and then analytically continue observables. So you have to know how your observables depend on mu. Analytically continue observables to mu squared equals is positive here. And this can be done for basically any thermodynamic quantity, because thermodynamic quantities typically depend on mu squared. So that is all well defined. So in a way, this is very similar to the Taylor series, but rather than just doing simulations at mu equals 0 and getting the Taylor coefficients from this point, you have access to this whole line here. So you have, in a way, possibly more control over the analytic continuation. Now, there's a lot more to say about imaginary chemical potential. We'll do that in the remaining time and tomorrow, because actually it's much more interesting what's going on here than just this line. So I have a 5-minute break now. This analytic continuation. So this expansion may have a finite radius of convergence. And so it's limited by some singularities in this plane here. And actually, we know there are singularities in this plane at negative mu squared, and we'll discuss that later today or tomorrow morning. So we know there are singularities. If there's a critical endpoint on this side, there will be also a singularity here. And so in any case, this will have a finite radius of convergence. In principle, you could look at all the higher order coefficients, mu to the 4th, mu to the 6th, and then somehow learn something about the radius of convergence from the coefficients in the Taylor series. But in practical terms, you have to go to really high order to see something, and up to mu to the 6 and mu to the 8 is not high enough to just look at ratios of these C to N's to read off something about singularities here. So for now, this is just used, say, to low order in mu, where you don't see any problems of singularities. Okay, so today and first lecture tomorrow, we're going to talk a lot more about imaginary chemical potential. And also the relation with the quark mass dependence of the phase diagram. And with a global symmetry of gauge theories and approximate symmetries for QCD, which is called center symmetry. So all these things are related, in kind of an interesting way, so they all go back to the phase diagram. So to get started on this, let's start with the easiest case. So we're going to start simply at mu equals 0. And we're interested in the order of the phase transition. So order of the thermal phase transition. And we are theoretical physicists, most of us, so we can change the quark mass and see how the order of the phase transition depends on the mass of the quarks. And this is often plotted in something called the Columbia plot. So I'm going to draw this graph here. And so what's on the axis here is the quark masses. So on the horizontal axis is the light quark masses, the light quark mass of the light quark, so up and the down quark. And on the vertical axis here is the mass of the strange quark. So we look at the dependence on up, down, and strange. So 3 flavors. Now, what do we know? So we have to link it to, so phase transitions are often linked to symmetries because we want to have define an order parameter, and order parameter 0 in one phase, non-zero in the other phase, and susceptibilities diverge when you have a phase transition, so we want to define something like that. So let's do the easiest case. What if all the quarks are massless? What kind of symmetry does QCD have then? Chiral symmetry, exactly. So in the massless case, we have chiral symmetry, and we have an order parameter, which is like the chiral condensate. And so it turns out that the transition is a first order transition. So here it's first order. Now when you turn on the quark masses, it stays first order, so it's not immediately destroyed. So there's a region here, I'm just going to draw it like this, where the phase transition is first order. If you turn on the quark masses even more, at some point you destroy this first order nature and it becomes a crossover. And this is like, think about a double well potential, say if you, or Ising model in external magnetic field, if you twist it too much, basically there's no more two competing minima, but it's just only a crossover. So that's the 0 quark mass case. What about the infinite quark mass case? So if I make all the quarks infinitely heavy, they essentially decouple from the theory. And so I just have a pure SU3 gauge theory here. So the quarks have decoupled. Does anybody know what exact symmetry SU3 gauge theory has? That tells us something about phase transitions. Z3 symmetry, exactly. So this is this center symmetry. So again, there is some kind of region here where we have this Z3 symmetry, which is an exact symmetry for the pure gauge theory and approximate if the quarks are, around but very heavy. And again, this region is first order. And the boundaries then between those two are second order. So here we have second order lines. And in the middle, it's not a real phase transition. So there's no singularities in the partition function, or susceptibilities do not increase without bounds, but it's what's called a crossover. And so the physical point, say, is in this crossover region. So this would be, where we are, say. So in QCD, in nature, the phase transition is a crossover. Now this line here hasn't really been, this is still open, so it could go like this, but it also could. So this region here is still a question mark. to sort it out actually requires, so this region is kind of done and dusted, so this is understood. It's also a little bit boring because it's heavy here, so there's no relation to nature, say. This region is interesting, but to study this region here, or this region here, you need really light quarks. So if you want to study this numerically on the lattice, you need quarks which are much lighter than in nature. So it's very difficult to study this region here. Okay, so this is the Columbia plot, and so we can vary all these masses and see what happens with the transition. And what we'll try to do now, but not immediately, is to include chemical potential now in this Columbia plot. So to extend it to have a chemical potential as well. Okay, any questions about this Columbia plot? Okay. So to go towards chemical potential, we first have to talk about this center symmetry, or Z3 symmetry. And so we do this in the pure gauge theory. So this is the case where all the quark masses are infinite, so they decouple from the system. And this, for notational purposes, is convenient to do it in SUN gauge theory, so I can write n explicitly in the equations, although of course n equals 3 when we're, apply it to QCD. So what is this center symmetry? It's a global symmetry. Not a local one. So what can we do? We can multiply with a phase. And this phase vector we call Z is e to the I, I'll call it Z to the power k as e to the I pi, so equal to 2 pi I k over n. And so k is an integer 0 to n minus 1. So I can have n different phases. Now these phases are actually elements of SUN, because they essentially, I can define them to live on the diagonal of a matrix. So like this. So if I take the determinant matrix where the phase vectors live on the diagonal, so it's an n by n matrix. It's just a product of the phases, and because it's pi I times an integer, the determinant is 1. So these matrices, these phase vectors, when viewed as matrices, have determinant 1. So as SUN matrices, they're part of the group. And since they're abelian, they commute with all elements of SUN. And so they form the center. This is called the center. Or Z. Zn. So these, so I can multiply every group element with these phases. It commutes. They form the center. And if I think about the action I have, say it will be actually invariant if I do this. So the action is invariant under a center transformation. Because I didn't give it in too much detail, but the gluonic action has these links going around, and if I multiply all the sites on a given time slice, what am I saying here? They all cancel out. What am I saying? Let me check. It leaves it in there. What am I doing? Each temporal link. Each temporal link. I'm multiplying each temporal link on a fixed time slice. That's it. Exactly. So if I multiply, so the action is built out of these plaquettes. So if I multiply this link and this link, which actually goes in the opposite direction, well, let me put the arrows in the right way. Up, up, down. That's it. So if I multiply each link in a time slice, I have on this side I have a z to the k, but on this side I have a z to the minus k. So that's 1. So the action is invariant, and in the same way the measure in the path integral is invariant as well. Because if I multiply the links with this center element, we've just seen that the determinant of the center is 1, of center elements is 1, so it leaves the measure invariant as well. So the measure transforms simply by multiplying the links. So the Jacobian is the determinant, basically. So the action and the measure are invariant, so this is a symmetry of the action. However, not all observables are invariant under this center symmetry. And in particular, there's one that's very important, which will change under a center symmetry. And that's the Pollak of Loop. So what's the Pollak of Loop? The Pollak of Loop is basically the product of all the links in a temporal direction which wind around the lattice. So in terms of equation, so it depends on position x here. P of x is 1 over nc, and then the trace, and then the I'm now writing the element as an argument of the function. So this means I take all the links in the temporal direction at a given time slice, at a given space point x, and I multiply all these links along the time direction until I'm all the way at the other end of the lattice. So this is NT. Now this quantity is gauge invariant. So this is a quantity I can study. It's gauge invariant because on the gauge symmetries all the links change to omega, omega, omega dagger. And because I have them in a trace here, all the omega and the omega dagger in the product will exactly cancel out. And because I take the trace, the last one will also cancel out against the first one. So this is gauge invariant. However, it is not gauge invariant. It is not invariant under a center transformation, because under this so if I multiply all the links on a given time slice with this phase factor, say I multiply this link here with the phase factor, that will not be compensated. And so the Pollak of Loop will change. So P at some given space point will go to, say, Z times P, or Z squared times P, depending on with how many links, how many phase factors I use. So it's not invariant. And that tells you, by the way, that it's not a gauge. The center transformation is not the same as a gauge transformation, because Pollak of Loop is invariant under a gauge transformation. Now, what is this? Why is this useful? Why are we interested in this? So if the expectation value of the Pollak of Loop is non-zero, then it will change value under a center transformation. Whereas if it's equal to 0, it will basically remain 0. If I multiply 0 with a phase factor, it will remain 0. And so the Pollak of Loop is 0, non-zero is actually the order parameter we're interested in. And if it's non-zero, it breaks center symmetry, or center symmetry is broken. Whereas if it is 0, center symmetry is unbroken. So it's an order parameter. So Pollak of Loop is an order parameter under for center symmetry. And its center symmetry can be spontaneously broken. Now, there are a few ways to see that indeed center symmetry is broken at high temperature. So the easiest way is to think about just perturbation theory. So what is perturbation theory? It basically means that all the fields, all the vector potentials, say, are small. If fields are small, you can do perturbation theory. So vector potentials are close to 0, but that means that links, which are e to the I a nu, links are close to 1 then. So if fields are small, links should be close to 1. So perturbative QCD corresponds to links being close to 1. But the Pollak of Loop is exactly the product of all these links. And so if this is the case, we expect, say, the Pollak of Loop also, the expectation value of the Pollak of Loop to be close to 1. Now, when is QCD perturbative at high temperature? So the first expectation is that at high T, the expectation value of the Pollak of Loop is non-zero, and so the center symmetry Zn is spontaneously broken. It is spontaneous because the center symmetry is a symmetry of the action and the path integrals. I haven't put in any explicit symmetry breaking to make it happen. It's spontaneous. Now, this relation with perturbative QCD or perturbative pure gauge theories can be made a bit more precise. By linking the Pollak of Loop to essentially a heavy quark. So, yeah.
You said that the center transformation is SUN transformation.
Well, the elements are elements of SUN.
It's
SUN. But it's not a gauge transformation. Because it doesn't do this, it's not of this form. So the links under a gauge transformation transform like this. Yeah.
So it's the action that is different, not the effect.
Yeah. So the action is invariant, but say the Pollak of Loop, which is gauge invariant, is not. Yeah. So to make this a little bit more precise in terms of center symmetry being broken spontaneously at high temperature, and I haven't told you yet, but it's unbroken at low temperature, we have to link the Pollak of Loop with heavy quarks. Because what is this Pollak of Loop? It's essentially the world line of an infinitely static quark, an infinitely heavy quark or a static quark. So So think about the hopping that we discussed earlier in the fermion action. This is just a heavy quark which sits, doesn't move in space, so it's infinitely heavy. And so the world line of a static quark is exactly equal to the Pollak of Loop. And in the same way, so this would be P, and in the same way I can have an anti-quark corresponding to P dagger going in the opposite direction. So this is an anti-quark. And so what I can then study is the correlation between a heavy quark at point X and a heavy anti-quark at point Y, and compute the expectation value of this combination. So this will be the expectation value of two infinitely heavy quarks and anti-quarks. I want to study their correlation. And this would then give you the free energy pair, a function of R, where R is the distance between X and Y. So this is free energy density of a pair of heavy quark and anti-quark. Now if I take X and Y far apart, then these quarks will no longer feel each other because they're screened by glue, say. So in the limit where X minus Y, or the distance, goes to infinity, it grows very large, this product here, this correlator will just become equal to the product of the expectation values. Like this, so this is like a... So I'm not taking only the connected piece, in other words, I'm taking the full expectation value, so only the disconnected piece survives. And since this is the complex conjugate of the other one, this will just be the expectation value of the Pollak of Loop.